Well, first of all, I'd like to thank Jim and the organising committee for giving me the opportunity to talk to you today about this new development, and also to thank our developing partners, which is Elastomold, which is part of the Thomson Betts Group over in the United States. Traditional technology, which is used currently in flood-proof type switchgear, tends to look like this here. Hermetically sealed units. These are stainless steel tanks. They'll have a tapered bushing on the top to connect the cables to, and generally they'll be filled with either oil or gas, SF6 gas. They're quite bulky, they're quite heavy, and of course they're difficult to maintain because they're designed to be sealed. If we look from a designer's perspective, we have to adhere to a number of different specifications when we're designing switchgear. The most important ones are the IEC 62771-100, and in America the equivalent would be the ANSI C37-74. If we concentrate on what these specifications say specifically about weatherproofing or floodproofing, in IEC they refer to this diagram here, which is effectively showering the equipment with water, and that the equipment must sustain or maintain its voltage during that shower. Whereas in ANSI, they state that the manufacturer must offer the purchaser some form of appropriate test results to back up their claim that the equipment is submersible or waterproof. So the standards are fairly vague and open as to what we can do. We already have some extreme environments that we have to design to, namely minimum and maximum temperatures, which are specified. Of course, if it's outdoor equipment, it may be subject, if it's in cold climates, to icing up. In the hotter areas of the world, we have to deal with high humidity, and we also have to deal with corrosive pollutant rainwater, which can rot the equipment. As a designer, I have some tools to enable me to design my equipment, to test it virtually before I produce a prototype. These are FEA type tools which we can use. We can heat the equipment up and we can see the effect of airflow over it and so on. So we do have more and more tools available to help us design new products. We've got some new extremes. Somebody mentioned earlier on there seems to be more earthquakes happening. We've already seen in the UK a number of flood incidents which has caused damage to the network, and we are now using more and more electric transport systems. There's a huge move for investment into high-speed trains, for example. Earlier this year, the PIT report stated that the collapse of the electricity infrastructure has a cascading effect on other damage that's caused through our cities. For example, we can't control the mobile phone networks. After half an hour, the mobile phone network collapses. This leads to the general public panicking slightly. We have people getting in their cars, driving down the roads, and we lose the traffic light system. That then means that the emergency services get gridlocked and can't get to the sites where they need to. It also means the electricity company engineers can't get to the sites as well, and their battery backup systems fail. So controlling the network becomes difficult. So, as a designer of switchgear, I have to take all that information on board. I look at what's happening in the world, and I come up with new ideas. I forgot, did I pass you? Yeah. One of the items I passed around was a small cardboard box, and inside it, Mo, if you'd let it go, is the euro note. I put a euro note in because it's slightly stronger than the pound at the moment. There are two magnets on there, and they've led to the development of a mechanism which is highly reliable. It's a magnetic actuator mechanism. We're seeing more and more of these types of mechanisms being used on switchgear now. The magnets are extremely strong. They have a life about 100,000 years, but they enable us to produce a circuit breaker which effectively is maintenance free. We use vacuum interrupters, and we use a mechanism which only has one moving part. So statistically it's more reliable, but it is genuinely maintenance free and can do many hundreds of thousands of operations. The second toy I passed around you was a modular circuit breaker, and that is quarter scale. What we've done, together with Elastimalt, is we've used their technology, which is to use EPDM rubber insulation systems over-molded by a conducting layer to create a circuit breaker pole, and then we've added the EPS magnetic actuator mechanism to create a circuit breaker which is maintenance-free. Both of these technologies are field proven, but this is the first time that they've ever been brought together. One of the areas of interest for Elastimalt was to use this type of circuit breaker in voltage substations. This is something that is not common in the UK at the moment. The voltage substation effectively is an underground substation underneath the walkway. As you can see, the access is fairly small. You can see the engineer is down in the vault. The cables run from a cable duct up to the circuit breaker and back out. In this circuit breaker, there's no gas or oil for the insulant. It's all done by solid dielectric mediums. Thousands of these cable joints and elbow connectors are in service already. It's a reliable technology. The whole circuit breaker is lightweight, and it's easy to install. The main breakthrough has been in the development of the bellow, which is shown here. Our claim to create a truly solid dielectric circuit breaker, we've had to get rid of any possibility of a dielectric stress occurring across a gas medium or a liquid medium. In this case, the only area where there's gas is below the vacuum interrupter and between the flexible rubber bellows, which houses the drive insulator to the switch. On the right-hand side, this is conducting. So we've created a Faraday cage. In other words, there's no voltage across that air gap. On the left-hand side, of course, it's insulating. The blue structure on the outside of the switch is a conducting layer, and then we have a semiconductor going through to full insulation where the cable connectors are made to stress relieve that joint area there. Because of the nature of magnetic actuators and the nature of this insulation switch, we can look at various different applications. It's very flexible. It can be mounted on a wall, it can be mounted on a pole, it can be mounted upside down on its side. There are a number of accessories as well that come with this, enabling us to automate this. We have voltage detection. You can see on the bottom picture on the left there's some yellow cables, so we can detect which side of that switch has got voltage on it. So if we want to do simple loop automation schemes, we can couple this up to the controller system. We also have current measuring CT blocks which can be added. These can be retrofitted after installation as well, because the cables are simply unpluggable and pluggable back on again. It's very compact. The model that I sent round to you there is in fact quarter scale, and this is a 38 kV circuit breaker. For those of you not familiar with circuit breakers, a 38 kV traditional design circuit breaker would be about the size of that speaker pole there. What we're talking here is because we're able to condense that high stress voltage across a solid dielectric, we're able to compact to approximately 1/3 the size of a traditional circuit breaker. We also have higher ratings. We're recognizing now that with the distributed generation schemes that are going on, people are adding loads, adding supply points and generators. So we're now increasing the capacity of the switch to be able to make against 40 kA fault current levels. So this new type of switch is designed to have certain cost benefits. It's got a low-cost insulation system which is highly tooled up. It's suitable for being manufactured in high-cost labour areas. It doesn't need cleaning. It conducts on the outside, so we don't have the problem of insulators requiring regular maintenance and cleaning and dedusting, and therefore it has a low lifetime cost. You can't maintain anything on this device. You can't maintain the vacuum interrupter because you lose the vacuum as soon as you try to. It has a small footprint. The small footprint itself means that effectively it has a low real estate cost where the site is. You can also put more switches in to that square foot area than you can with traditional designs. And of course it has inbuilt monitoring because it's got the add-on accessories so that we can keep it inspected from a distance. The other big advantage of having the insulated outside of this type of switch means that there is no dielectric stress over the switch itself. It's all compacted, which makes it suitable for flooding. The device that we've got at the moment can sustain its electricity path to a depth of about 3 meters. Now, the problem isn't the fact that we can sustain the integrity of the device under 3 meters of water. The problem is what that water's got in it. We know from previous incidents in Carlisle some years ago, and from the earlier presentations, that it's what's in the water, the sewage, the debris, the floating elements that come along in there, that actually cause the later problems. They're the things that cost us the money to clear up and that take a long time to do so. So, this switch is suitable for hostile environments. It's high vibration resistance because of this very high powered latching mechanism. It's chemically resistant. The EPDM rubber performs against most corrosive materials. If you were to submerge it completely in petroleum or oil, then you would probably only get a year or so's life out of it, but you wouldn't have that situation for most of the sites. The fact that it has a minimum amount of organic material in it means that if there is a dielectric failure, there's less likely to be a large explosion. What tends to happen, if I briefly show you the model, it has got some pressure relief system, and if there is a dielectric failure, as my American colleague says, it burps. The rubber expands and relieves the pressure through a vented area. If you compare it with a gas-filled switchgear design that explodes, you'd have much more damage to the surrounding substation. We believe that there'll be more and more people travelling by trains, for example, in the future, as fossil fuels become more expensive. So we're looking at locomotives for one of the applications. Locomotives have their own problems, travelling at high speed, 300 kilometres an hour plus. They have high duty cycles in comparison to normal traditional switchgear. For example, the trains that travel up and down the west coast would be expected to do, the circuit breakers would be expected to do 1 million operations on them. And of course, more and more trains are becoming all electric. If you put a compressed air system onto the train, it's taking bums off seats, it's occupying space. And now the new trains are using regenerative braking schemes. So the idea is to create new all-electric systems. The trackside equipment itself has problems. Equipment mounted on gantries is subject to flying debris, which is picked up by the train as it goes past. The wind shock causes circuit breakers to trip as well. And of course, there's high vibration again. We've looked at offshore wind power as an application for this device. We've already seen how inaccessible these sites can be. The compactness of this switch means that it can be mounted inside the tower. It's very inert to the hostile environment, the salt fog environment that goes around in these areas. And of course, it doesn't need any maintenance, so the site visits can be reduced. And here is a picture of a tidal type power generator. Again, it has all the other problems that the offshore wind power generator has, but also it's subject to high vibration. So switches of this nature can sit comfortably on this type of structure without delatching and opening the circuits. The mechanisms, as I said, are all very well proven, and I've talked about the vibration incidents on a number of the slides. One of the areas where we're winning at the moment is that our circuit breaker designs are being used on military applications. Really, this is just a proof of the confidence that certain industries already have in our technology. The tests that were done on the circuit breaker that goes in this new frigate showed that the vibration test went up to 70 G, and the circuit breaker sustained those shock loads. So, in conclusion, the developing industry of the medium voltage area that I'm in is looking at some of these problems for the future. We've got materials available to be utilised to help produce products which can meet some of the disasters that we've seen over the last few years. And the applications that these products can go in are far-reaching. Thank you.